Last time we started with section 6.3 and we were looking at the multiplication and division of rational numbers. We talked about some properties and we had done one example, or I should say the last example we did was this one. Here, which lights? Okay, I think that's the combination we want. Okay, and we look at things about reciprocals and inverse relationships, multiplicative identity, and the property of equality, all coming into play there. And we're going to do another one right here that's a little bit more involved, partly because there's more pieces and also because the denominators are less friendly at matching up quickly. So we have a 3, a 4, a 6, and a 2. For our denominators, our directions say to solve for x, and then identify the properties that we're using as we use them, which is kind of the directions we had last time. All right, so a suggestion. What do you think that you might want to do first? There's more than one right answer. So somebody give me an option.
Put the x's on both sides.
Okay, move the x's to the same side. I'm going to move mine to the left. But it doesn't matter. So I'm going to go with minus x over 6. As I do that, that's a property. That's two properties actually in one. The properties that we're using as we do that are the additive inverse property. That's why we chose the value we chose. And we're using the addition property of equality, which is what allows me to do something to both sides of an equation and it remain unchanged. Okay? So that's our first steps. And I have 2x over 3 minus x over 6 plus 1/4 equals negative 1/2. Those add to 0. Now, the fact that I was able to cancel that and add those to 0 is actually, and that the 0 disappeared, is the additive inverse property and the additive identity property. The additive identity property says that when two of these things are added together, we get 0. But if 0 is added to something, then it actually remains unchanged, that value. So 0 minus 1/2 is just the negative 1/2. All right, what else do I need to do besides simplifying a whole bunch of stuff in general? Emily?
Move the 1/4 to the other side of the 1/2.
Yep, so we're going to subtract the 1/4. And as I do that, I actually have those same properties from the very first step repeated. It's the additive inverse and the additive property of equality. Okay, and I'll rewrite again. I have 2x over 3 minus x over 6 equals negative 1/2 minus 1/4. Okay, everything's shifted to sort of a good location now. It's a great first steps to do. Now I need to get them to combine where they are. So what am I going to have to do on the left to make that happen? Common denominators. And not only on the left, but on the right-hand side as well, of course. I need common denominators to make this happen. Now, because I have a 3 and a 6, it might not be my best idea ever to just multiply the 3 and the 6, although it could, and it wouldn't be a bad thing to do. I get 18. It's not a crazy huge number. But if you happen to recognize before you do that, that 3 times 2 is 6, you can keep the numbers a little bit smaller and get a common denominator that way. So I have 4x minus x over 6. I can do the same sort of thing on the right-hand side. What do you notice between the 2 and the 4? The 2 times the 2 would give me a 4. So I can do the same thing that I just did on the left-hand side. That leaves me with a 2 on the top minus 1 over 4. So what are we doing as we approach that steps? Well, we're getting common denominators, right? And as we're doing that, we're actually multiplying the top and the bottom by the same value. Multiplying the top and the bottom by the same value is the multiplication property, what do we call it? Multiplication identity property. That's the word I wanted there. Okay, when I multiply the same number in the top and bottom, that's equivalent to multiplying by 1, right? That's what I really did. I multiplied by 1 on the left in the form of 2 over 2 and 1 on the right in the form of 2 over 2. Yes?
Would it be the negative 2 minus 1?
Did I mess something up? Yes, I lost my negative because I squeezed that in there. Thank you. Okay, 4x minus x is 3x over 6. And then negative 2, as you pointed out, minus 1 would be negative 3 over 4. You have a couple of different options at this point. What would you do next? Simplify the 3 over 6. That's a good next step. Certainly doesn't have to be done, but it'll make things smaller. And I'm a fan of making things smaller. So I think that's a good plan. We can reduce this by dividing each of them by 3 is what we're really doing. So this is 1/2. So I have x over 2 equals negative 3 over 4. And doing that right there is another property of the multiplication. It's another example of the multiplication identity property. Because I'm multiplying by 1/2, which is the same as multiplying by 1/3, which is the same as dividing by 3. Again, I have a couple of options here. What would you do? What would you do?
Multiply I guess both sides by 2 over 1.
Yeah, I think that's a good next step. Certainly not the only one, but it's a really good one. I currently have my x divided by 2. So if I multiply by the reciprocal of that 2 in the denominator, I would get 2 on either side. So again, this is happening because we're using the multiplicative inverse property now and the multiplication property of equality. Both of those are playing in there. When I do this on the left, 2 over 1 times x over 2, those 2 over 1 and the over 2 are going to cancel, right? And it's going to leave me with x. As I do that, that's the multiplication inverse and identity properties. It's a multiplication inverse because 2 over 1 times 1 over 2 is 1, and identity because 1 times x is x, and I'm left with just x. On the right-hand side, I have negative 3 over 4 times 2 over 1. What will that give me?
Negative 6 over 4.
Okay, that's one version of it. And what would that simplify to? Negative 3 halves. And if you happen to recognize it a step earlier, you could reduce these so that you never went to the 6 over 4. You don't have to, but it's another option. So this is my final answer at the end. And we're just using like the definition of multiplication as that last step. I'll write that in as the very ending things. That says definition of multiplication. Sorry, running out of space for sure. Okay, so we're about to look at division. Y'all ready? All right. Division of rational numbers. Here we go. If a over b and c over d are rational numbers, and we're dividing a over b divided by c over d, it is equal to e over f if and only if e over f is the unique rational number such that c over d times e over f is a over b. So jot that down, and I'll do some just whole numbers so you can see it work out what it's telling you a little bit more directly. Okay, so let's say we had 6 divided by 2. What is 6 divided by 2? 3, absolutely. The reason that 6 divided by 2 is 3 is because 2 times 3 is equal to 6. That's why. And that's what you're seeing happen here. This answer, E over F, if it is multiplied by the C over D, right, E over F times C over D, I get back to the A over B in the beginning, just like the 2 times 3 gets me back to 6. That's what the definition is saying, is that this is an inverse operation of multiplication. The division of rational numbers has an algorithm as well. So the algorithm that we apply when we're dividing rational numbers actually talks about multiplying by reciprocals. So when we have A over B divided by C over D, we can change it to be a multiplication problem. And when we do that, the second fractions turns into its reciprocal, right? It flips. So you see the C over D become D over C. But I'd like to show you why that happens, because it looks a little bit like it's just, it's very nice, convenient, fine, you can do that, but like, is it really, you can do that? Why would that actually work? And it's not very difficult to see why, so I'd like to show you this. So when you have that one kid who says why, at the very least, you will have seen it before, and you can figure it out again, or go back and find it somewhere. There is a why. Okay, so instead of writing this as division like this with this division sign, I'm going to write it in fraction form. So it's going to look like A over B divided by C over D. Everybody good with that? It's ugly looking, but you've seen that before. We call that a complex fraction, where we have fractions inside of fractions. Okay, well, I don't really want the C over D down here written this way, right? So I use the reciprocal of C over D to let it become 1. If I can make the denominator 1, I eliminate the fraction in the denominator. So I'm going to multiply it by its D over C, because what I want this to become a 1 down here. But in the bigger fraction, in order to multiply the denominator by D over C, I have to do it to the numerator as well. So far, so good. So my denominator is now a 1, that I'm going to move over. And my numerator is A over B times D over C. And when we divide by 1, it doesn't change values. So we're left with A over B times D over C, which is exactly where we were headed. Okay. It has to do with the multiplicative identity and the multiplicative inverse of the value C over D. That's what's happening there, is that I'm using those properties and are at play and showing why that works. Okay. So my family is about to go somewhere tonight. We're going to go to City Bites, and they got those big giant cookies. McAllister's has the big giant cookies. Crumble has the big giant cookies. You get sick if you eat the whole cookie. You know what I'm talking about, right? Okay. So I want you to have that image in mind, those big giant cookies, as we do this particular problem. So we're going to describe what's meant by 6 divided by 2 and show a diagram to support that. And then we're going to use that same idea to talk about what it means to do 6 divided by 1/2. Because I can tell you that 6 divided by 1/2, I could just flip it, and that's fine. But there's got to be a reason behind it with the values that they really are as well. And there is. So we're going to look at 6 divided by 2 for starters. So we're going to imagine we have those 6 large cookies. We will not have 6 of them when we get together this evening. Okay, all of those are now a little bit too big for me to actually make this work. Let's try again. Okay, there's 6 of them. I'm going to show you 2 different ways to describe what's happening here. So I'm going to draw the 6 cookies twice. Okay, in the top diagram, what I'm going to do is I'm going to split the cookies into groups of size 2. So if I do that, I have one group of size 2 here, one group of size 2 here, and one group of size 2 here. So my mindset when I'm doing this is I want groups of 2 cookies, right? So this is what I did the other day when I took Oreos and put them in bags in my kitchen. I wanted the bags to be a specific size, right? I want a specific number of cookies per bag. So I want 2 cookies per bag, and the answer to this question then is 3, and it's answering the question of how many bags did I use? How many groups did I make? The other way to take a look at this division is to talk about splitting this into into 2 groups. So instead of groups of 2, I have 2 groups. So this image is, I've got 6 cookies, and I have 2 people that are going to get the cookies, right? So it's not based on how many cookies I'm going to give them, it's based on the number of groups that I want at the end. And this is exactly what happens when people make groups inside of a classroom. You have to decide, do I want there to be a specific number of groups so that there's one of me and I can get to each of the groups? Or do I want the groups to have a specific number of people so that the groups don't get too large or they're large enough? Right? These are the decisions you make. And sometimes it's one and sometimes it's the other. They're both valid. But when I do this and I split it into 2 groups, right? On the first one, I have groups of size 2. And on the second one, I create 2 groups. And the answer to the question 3 answers, how many does everybody get? So there are actually 2 people that are getting all these cookies. How many of them do each, I'm not saying this right at all. How many cookies does a kid get? That's what I'm talking about, right? How many do they get? Well, here they would get 3 cookies. Okay? Now I'm going to do the same picture over here, the same 6 cookies, but I want to divide them by a half. Now, the second way that I divided them over here, which says, I want to create 2 groups. It doesn't work very well here. I want to create half of a group. What does that mean? I want to create half of a group? It doesn't work. But the first way that we described it, I want to create groups of size 2, works really well here. Because I can create groups of size 1/2. What do I have to do? Split each cookie, right? If I split each cookie in half, I create 2 groups, 4 groups, 6, 8, 10, 12. I have groups of size 1/2, and there are 12 groups. And notice, if you had taken 6 divided by 1/2, and you used the property that we did before, where we turn it into multiplication by the reciprocal, what will you get? 12, just like we did from the picture. It's got to make sense. If it doesn't make sense, then we got a problem. Okay, groups of size 1/2. And nobody gets sick, because eating half of one of those cookies works just fine, right? Just fine. Okay, we're going to shift gears. The other part in this section is actually a continuation of something we do in chapter 3. So if you've had number theory, you've seen a portion of this before. If not, it's not going to hurt you. But this is a continuation with an extension onto it. So we're going to take a look at exponents. So definition of an exponent, if we have a rational number a and a natural number, remember natural number means the counting numbers 1, 2, 3, 4, and so on, n, then a to the n means a multiplied together n times. So a cubed is a times a times a. That's what we mean by this notation. It's repeated multiplication. Now there are 6 theorems of exponents. That's actually more than we have back in chapter 3 because of what we've done in chapter 6 and developed a bigger type of number system with fractions. So first thing I'm going to do is I'm going to just show you what the properties all are, and then I'm going to justify for you why each of them work for the exact same reason that we justified the division part before. There's a reason behind it. It's not hand waving. It really all works. okay? So the first one is a to the m times a to the n. So when the bases match, you can add the exponents together. This is a to the m plus n. On number 2, when you divide them, bases matching, we can subtract the exponents. 3 looks like 1. We've got an m and an n exponent, but it's missing another base. It's a single base a. There's not 2 of them listed. So when we have a base a raised to a power and then another power on the outside, we multiply the powers together. 4 and 5 are very similar. We actually have kind of like a distributive property with that power of m. AB to the m is a to the m, b to the m. And the same thing for division, a to the m over b to the m. Number 6 and number 5 are also quite similar. The only thing that looks different at the get-go is that this has a negative exponent here instead of positive. So the m goes through just like normal. The negative flips the fraction. So instead of having a to the m over b to the m, we end up with b to the m over a to the m. Okay, so let me justify those 6 properties, and then we have a couple of more that I'll present too. All right, so this is supposed to be addition. That's the property, right? So here's why it works. And these are not proofs, but there's one of them that's going to be a proof later on. But they're just justification with some examples. You can see by example that it makes sense. So let's say that we had a cubed and a to the 4th. What does a cubed mean? A times a times a. 3 of them. What does a to the 4th mean? Yeah, a times a times a times a. 4 of them, right? There's 3 here, there's 4 here. How many a's are there? 7. So this is otherwise known as a to the 7th. And how in the world do you get from 3 and 4 to 7? You add. And you can see it work. Very concrete example. And to be honest, a concrete example would justify for your kids probably better than a proof with genericness would anyway. So these are really good tools to have. This next one's supposed to be division turning into subtraction. So let's say that we had a to the 5th over a squared. So a to the 5th means 5 a's. A squared means 2 a's. One of our properties of fractions allows us to reduce common factors when they're being multiplied. So this a and this a can cancel because each of them are being multiplied by the other pieces. And we can do it again. That leaves me with a. How many a's is it? 3. And how do we get from 5 and 2 to 3? We subtract. Number 3, we're supposed to be multiplying the m and the n. So let's do that same 3 and 2. I guess not the same. I didn't choose that before. We'll do a 3 and a 2 this time. So a cubed means I have 3 a's. And the squared on the outside means I have the same 3 a's repeated. So I have a. How many a's are there? 6. And how do we get from 3 and 2 to 6? We multiply. Number 4 says that I should end up with it like this, a to the m, b to the m. So we're going to do AB cubed. So cubed means I have AB times AB times AB, like that. One of our properties of real numbers is we have the ability to switch the order of multiplication, that's called commutative, and to regroup things, and that's called associative. We'll talk more about them in other sections. It keeps coming back up. But those are properties of real numbers. So I can regroup so that my A's are all together, and then my B's are all together. And then I can quickly see that this is A cubed and B cubed. And you can see that it's, quote unquote, distributed the power of 3 through. Okay, last two. It's supposed to be A to the M over B to the M. So we're going to do that same cubed. It's actually easier to see on this one. So A over B cubed means I have A over B times A over B times A over B. If I multiply straight across the top, I have 3 A's. Straight across the bottom, 3 B's. 3 A's is A cubed, and 3 B's is B cubed. And then our last one. It's supposed to flip the fraction and distribute the m. So we have b to the m over a to the m. And I'll use 3 again. We'll do it as a negative 3. So the first thing I'd like to do is to separate the negative and the 3 from one another. I can do that because negative 3 really means 3 times negative 1. So I can separate them that way. I'm sort of breaking apart the 3, right, the negative 3. The a cubed, or the cube, will become exponents on the a and the b, so it becomes a cubed over b cubed. And then what my negative does is my negative means reciprocal, inverse, flip the fraction, whatever phrase of that resonates with you. They're all meaning the same thing. So I'm going to take my fraction and I'm going to turn it upside down. Now I don't keep, nothing's negative. I've dealt with the negative by flipping the fraction. So I end up with b cubed over a cubed. There's 2 additional exponential facts. A to the 0, do you remember what that one is? That's 1. And number 8 is quite similar to number 6. It's just a single value a to the negative n. And what this does is it makes it the reciprocal, 1 over a. I don't know why I put a parenthesis there at the beginning. 1 over a to the n. It looks like that. So this is my one proof. And you could replace my genericness with numbers if it made more sense to a child. We're going to start with a to the 0. The way we get 0 is that we subtract 2 values that are identical. I'm going to call them m and m. You could certainly say 3 and 3, or 5 and 5, right? That's 0. But if we use property number 2 in reverse, so property number 2, right there, in reverse, and we go from the right-hand side over to the left-hand side, I can turn m minus m into that division kind of notation. So this is a to the m over a to the m. And what happens when you divide 2 identical quantities? It's 1. And we went from a to the 0 to 1. And that's a legit proof. But again, if you don't want to use the arbitrary m's, use a number, and then you've got an example to do for a child if that would be more reasonable too. Our last one with an example, we're going to use that 3 again, a to the negative 3. So we're going to do the same thing that we had done before. We're going to separate the negative from the 3. So I have a cubed, and then I have the negative 1. So negative 1 means I flip it upside down, but I don't have a down. So I need to write it over 1 in order to do that. That's what that would look like. And then if I turned it upside down, I would have 1 over a cubed. Now the questions that we're going to see following this are all going to be using these properties. You don't have to justify anything anymore. I'm not going to ask you to prove or to justify any of these either. This is for your benefit for the future if you have that child, and because I feel like you should know that they really work. It's not just me telling you these properties that somebody created somewhere along the way and they don't make any sense. They all make sense, okay? What we're going to do, though, now is we're going to actually use these properties to write some expressions in simplest form. You'll notice some of ours will actually have variables in them, like A here, and some of them will have numbers in them, like B. And we'll be able to use these properties for both kinds. Now, all of our properties only allowed us to combine things and to simplify things that had the same base. So, for example, if I just had the numerator here, AB to the 4th, I can't do anything to make it any simpler or change it because A and B are different bases. But because I have an A on top and an A on bottom, that I can combine in some way because they have matching bases. So there's several things that I could do. I think I'm going to use property number 2, the one we just talked about, where we did the subtraction, back in that actual one that was a real proof. So it says that if I have A in the numerator with an exponent and A in the denominator with an exponent, I can subtract the exponents. What's the exponent on A in the numerator? It's a 1. So my exponent over here will be 1 minus negative 3. Not minus 3, minus negative 3. I'm going to do the same thing with my B. What will the subtraction exponents be here for B? 4 minus 2. All right, so what is 1 minus negative 3? Yeah, I end up adding. 1 minus negative 3 is 1 plus 3, which makes it A to the 4th. And what about for B? It's 2. I want, when I'm done, to have positive exponents, and this one has positive exponents, so it is done. Now, the next one is trickier in some ways because the numbers are there. It's easier with variables. You can't say that all the time, but with these it is. In order to combine things, I have to have bases that match, and 4 and 2 and 3 and 5 and 25, they don't have matching values right now, right? There is no number that is repeated as a number itself. Like, I realize there's a 5 in the number 25, but that's not what I mean. That's a digit. The number 25, the number 5, the number 4, the number 2, none of them match. But I can make them so that they do. And here's how. Right now I have 2 over 5 to the 3. The number 4 is 2 times 2, right? 2 times 2 means 2 squared. The number 25 is 5 times 5. 5 times 5 is 5 squared. And if I change them, like so, now I have some matching bases, right? Okay, there's a couple of different things that I could do. I definitely am not trying to figure out what these actual concrete numbers are when I'm done. I'm going to have it in exponential form. So we're going to be leaving this in exponential form. That's like the one cadence that you asked about in the last section. Should we just leave it that way? And I was like, no, here we are, because that's the point of what we're doing is exponent simplification. So we're going to leave them in exponential form. But what we can notice over here is that I have 2 to the 3. I can distribute that. That was property 4. And I have 5 to the 3. And I can do the same thing over here. It's a little bit tempting to say, oh, look, there's a negative, let's flip something. But it's not real helpful because it would actually be kind of nice if the 2's were beside each other instead of up and down. So I'm not going to move it. You could do it, but there's really no need. We can still take this negative 6 and distribute it in. So the negative 6 times 2 would be negative 12. So I have 2 to the negative 12. And if I have my negative 6 times the 2 on bottom, I have another 12, negative 12. Everybody good so far? Okay. So moving across the top, I have 2 to the 3rd and 2 to the negative 12th. what can I do with the third and the negative 12th? Add them, right? Yeah, 3 plus, I'll write it plus negative 12 that way. And on the bottom, I have the same thing, 5 is my base, and it's 3 plus negative 12. All right, so what's 3 plus negative 12? Negative 9. That's right. So I have 2 to the negative 9th, and it happens to have the same denominator, exponent of the denominator is the same, negative 9, 3 to the negative 9. This isn't quite done because the directions want it to have no negative exponents. Okay? So what we can do is anything that's a negative exponent needs to move. If it's on top, it moves to the bottom. And if it's on bottom, it moves to the top. Only if the exponents were negative. So pretend for a moment that the exponent on top were negative and the exponent on bottom were positive. If the exponent on bottom were positive, it wouldn't move. It'd just stay put. And what's on top would join it. Now, that's not what's happening in this problem. Both of them are negative. So we're going to move both of them. 3 to the 9th will be on top now, so it'll be a positive 9. When it moves up, it becomes positive. And the 2 to the 9th will be on the bottom because when it's... Oh, did I write a 3? Yeah, it should be a 5. Thank you. Let's get a 5 in there. 5 to the 9th will be on top, and then 2 to the 9th will be on bottom. Thanks. Okay, so here's what's going to happen. I have probably 7 minutes left to finish this section, and I really want this section done so that we can move on to 6-4 on Wednesday, okay? So I'm going to push pause on the video. I'm going to let you guys go. I'm going to go back to my office. I'm going to record the next, I think it'll be about 7 minutes, and then you can log in and you can watch those last 7 minutes before you start your homework, okay? Homework and group work will be due once this lesson is complete, all right? All right, this is the last little bit here of section 6.3. We're going to take a look at using some of these in contextual situations at the very end. Before we do that, we have one more example of how we're going to work with our exponential properties here. So you can see these are equations and inequalities. On the left-hand side, you have 2 to the n times 2 to the 7th. We can combine those as n plus 7. And then the 64, we can write it as 2 to a power. If you aren't sure what power it is, you can just take 64 and you can divide it. All right, so 64 is 8 times 8. And then 8 is 2 times 2 times 2. So we can break it apart like that. That's 6 2's. At this point, in order for these to be equal, because the bases are equal, the exponents must be equal. So n plus 7 must equal 6. And that will only happen if n is equal to negative 1. Right? Negative 1 plus 7 is 6. On the second one, we need them to have the same base as well. And 81, if we break it down, is 9 times 9. And then 9 is 3 times 3. So this 81 is actually 3 to the 4th, which stands a chance, but it's in the wrong place. It's in the denominator. But I can bring it up to the numerator by making the exponent negative. So it's a negative 4. Oh, sorry, type over there. That was supposed to say n. So I have 3 to the n is less than or equal to 3 to the negative 4. Again, because the bases match, we can take the exponents, and the exponents must be in the same relationship, that is less than or equal, that the original ones were. So this is n is less than or equal to negative 4. All right, if you take a look at number 8, this is not a problem we'd necessarily want to actually divide. It's awfully messy, right? 20 and 1/3 divided by 9 and 7/8. And if we were to divide it, how would we do that? Well, we'd need to get them into an improper fraction form, and then we'd flip the second fraction. We'd look for things that would reduce. It'd take a bit. But fortunately for us, this actually just says to approximate. And approximating this isn't bad at all. 20 and 1/3 is approximately 20. And 9 and 7/8 is approximately 10. And 20 divided by 10 is equal to 2. So this quantity is approximately 2. All right, number 9. On number 9, we have Jasmine, and she's reading a book. She has 1/4 of the book left. Maybe she knows that because she just sort of looked at the spine and she's like, it's about 1/4 left. Or maybe she's reading it in electronic form where she can see what percent that she has left, and she knows it's 25%, and that's number 1/4 as a fraction. However, she also happens to know that she's read 246 pages. She might be able to see that on an electronic device. Or if she's got the actual book, she might be able to see that it's 246 pages. And we're going to figure out how many pages she has left to read. Okay? So there's a couple of different ways to do this problem. We do want to recognize that this says 1/4 of the book is left, and this one says she has read 246 pages. So they're not representing the same number, right? She hasn't read 246 pages, and that 246 is 1/4 of the book. It's actually 3/4 of the book, because she only has 1/4 of the book left. So this 246 pages represents 3/4 of her book, right? Not 1/4 of her book. We can actually solve this by multiplying by the reciprocal. We talked about that before. If we multiply 246 times 4/3, we will get 328 pages. Now, it's important to realize we didn't answer the question, right? She doesn't have 328 pages left. That doesn't make sense. She's read 246. She can't have more of the book left than what she's read because it says she's read a lot of the book. She only has 1/4 of the book left. So what did she actually find? Well, this is actually the total number of pages, right? So what would we do to find the number of pages she has left? Well, we'd subtract 328 minus the 246 that she's already read, and she will have 82 pages left to read. All right, last example for today, example 10. Al gives 1/2 of his marbles to Hosea. Hosea gives 1/2 of his marbles to Isabel. Isabel gives 1/2 of her marbles to Letitia. If Letitia was given 4 marbles, how many marbles does Al have now? All right, so we're working with these fractions, but this is actually a really good example of problem solving in a general sense. And one of our problem solving methods that you might think about is a method called working backwards. So in particular, we will start with Letitia, and we'll work back to get back to Isabel, and then we'll work back to get to Hosea, and we will end with Al. So it says that Letitia was given marbles. It says 4 marbles. There it is. Letitia was given 4 marbles. But her 4 marbles all came from Isabel, and Isabel gave her half of what she had. So Isabel actually had 8 marbles, and she now has 4. Because she gave 4 of them to Letitia. But she started out with 8. Now, those 8 marbles came from Hosea. Hosea gave Isabel half of what he had. Well, that meant he would have had to have 16 because he has half of those, namely 8, that he gives to Isabel. But once he takes his 16, he gives half of them away. He now has 8. And then we have Al. Al had twice as much as Hosea because he gave half of them away, so he had 32. And he gave half of them to Hosea, and he now has 32 minus the 16 he gave away, or 16 remaining. The question says, how many marbles does Al have now? Al now has 16 marbles. Now, the question could have similarly asked us, though, how many did Al start with? And that answer would have been 32, right? So be careful with what you're being asked.